The goal of this video is to talk about conjugates, specifically in situations that are applicable in the calculus classroom. So in some circles, they're going to call this rationalizing. So just know if they ask you to rationalize something, this is what they're talking about. So the purpose of a conjugate, or how we're going to be using them, is we're going to use them to change into an equivalent form. So using conjugates would be a tool if the original problem that we're working with in the form that it's in is not helpful, but we could easily use a conjugate to get it in another form that would be helpful for us. So for example, this is probably the first situation you would have seen a conjugate before. Let's say if we had the square root of 3 plus 2 divided by the square root of 5 minus 1. And it's improper to have a square root in the denominator of a fraction, and so we would multiply by a well-chosen 1. We want to multiply by 1 because that's not changing what the fraction equals, it's just changing what it looks like. And that well-chosen 1 would be the square root of 5 plus 1 over the square root of 5 plus 1. And so that's the conjugate. When we multiply by this, what's going to happen is that denominator is going to get fixed. It will no longer have a square root. So to multiply these two, we have to FOIL the top and the bottom. So the square root of 3 multiplied by the square root of 5 is the square root of 15. The square root of 3 multiplied by 1 is the square root of 3. This 2 multiplied by the square root of 5 is 2 times the square root of 5. Simple. And then 2 times 1 is 2. Now on the bottom, if you look at this, you can see that this is the difference of squares. That's exactly what it is. So square root of 5 multiplied by square root of 5 is the square root of 25, which I hope we're all looking at and saying like, oh, yep, that's 5. And then we have the square root of 5 multiplied by 1, so that's a positive 1 square root of 5. And then we have the square root of 5 here multiplied by negative 1, so negative square root of 5. And then we have negative 1 multiplied by positive 1, so that's negative 1. So here what you can see is those middle terms cancel out, and because the conjugate has opposite signs, that will always happen. Those two middle terms will always cancel out. And just like we expect with difference of squares, the square root of this is what is in the parentheses, and the square root of this is what's in the parentheses. So if you want to shortcut that FOILing step, you are more than welcome. On the top, in the numerator, we don't have any like terms that can be combined. So I would just say this is the square root of 15 plus the square root of 3 plus 2 times the square root of 5 plus 2. And then on the bottom we have 4. All right, now let's go ahead and make sure that this is the same thing. So I'm going to go ahead and type this in. I have the square root of 3 plus 2. And I have the square root of 5 minus 1. And that's the decimal that it equals. And if I plug in the next one, I'm going to see square root of 15 plus square root of 3 plus 2 square roots of 5 plus 2 divided by 4. And you can see it equals the same decimal. So the purpose of a conjugate, we're not doing any mathematical solving or anything like that. All we're doing is we're changing it into an equivalent form that potentially would be easier to work with, or in this case, more proper and more difficult looking, I guess. All right, here is another example of a situation where you have seen this. In working with imaginary numbers, and this is basically the same because when you work with imaginary numbers, you're talking about the square root of -1. That's the definition of an imaginary number. Or you can say that I squared, an imaginary number squared, is -1. So here, again, the problem with this is that we have an I in the denominator, and that would be a square root. And so we would multiply by the conjugate. That would fix the problem. So 3i plus 7 divided by 3i plus 7. And again, it would be a similar situation. We would multiply out the top. So 15i squared plus 35i plus 6i plus 14. And then here we have 9i squared plus 21i minus 21i minus 49. So again, those middle terms cancel out just like we expected. And then here we have to remember that I squared is -1. So 15 multiplied by -1 is -15. 9 multiplied by -1 is -9. So on the top, we have a -15 and a +14. And we have 35i and 6i. And on the bottom, we have a -9 and a -49. And so that is -58. And so there's our expression there. Most math people would probably not leave that negative on the bottom. They would probably pull it to the top. So if you take that negative out of the bottom and move it to the top, it's going to change the signs of each of your top pieces. So we would say 1 minus 41i. Both of those answers are definitely acceptable. All right, so what I'm going to do is show you how this is the same on your calculator. So if we were to take the original expression, and you have an I button down here, but you can't use that fraction function that I've been using, you cannot type it in like this. Your calculator does not like that. So I'm going to go ahead and type in 5i plus 2 divided by 3i minus 7, and I'm putting the top in parentheses and the bottom in parentheses to show my calculator that it's a whole group. And I have the fraction form over here, so I'm going to get the fraction form on my calculator. And you can see it's actually the same answer, so it's kind of like the calculator gave us a common denominator of 58. So I've got 1 minus 41i divided by 58. So as you can see, it's the same thing. Again, I changed the form of what I was looking at. I didn't change what it was equivalent to. All right, now there's a third circumstance where you guys have looked at conjugates before. And I don't think I'm going to have you guys write down this entire problem. But the third situation that you might have seen conjugates in the past is in proving trig identities. So we're going to say this is the trig identity that we're trying to prove here. And, sorry, I'm folding my notes so I can show them to you without making you guys do the problem with me. So there's the original problem. And what I could do is I could say, all right, in this problem, I'm going to go ahead and I'm going to mess with the left side and try to make it look like the right side. So what I could do first is you can see I went ahead and multiplied by the conjugate. And again, you don't have to write any of this down. You can just kind of pay attention to it. So I'm multiplying by the conjugate, and if it was 1 minus cos theta, then I'm going to use 1 plus cos theta. On the top, I didn't FOIL them or distribute the cosecant theta. I just kind of wrote it out that those two things were being multiplied. On the bottom, when I FOILed those out, I got 1 minus cos squared theta. So remember, difference of squares is what this always ends up simplifying to. What I did next is I took cosecant theta and I wrote it in terms of sine. And when you look at the formulas or the identities or whatever, you can see that 1 minus cos squared theta is the same as sine squared theta. So I went ahead and put that on the bottom. After that, I went ahead and got rid of this as a fraction, so I just flipped the bottom up. So keep the top, change it to a multiplication problem, flip the bottom up. And when I did that, you can see that this sine right here and this sine squared right here becomes sine to the third. And so that means that we've completed our identity. our proof there. Now, the part of that, I don't need you to do every single step of it, but the part of it I want you to take away is that conjugates don't just show up in one aspect of math. They show up in lots of different circumstances, and they're a good mathematical tool that you should keep in the back of your mind because it could be something that would simplify. And that's what we're going to find in the context of looking at limits, is that conjugates are going to be one of the tools that show up pretty often.